So we're going to try and explore how to make sense of the tangent lines that we can find to a curve at a given point in a given direction, and also the tangent surfaces to these curves. Now, primarily when we speak of tangents and say functions of a single variable, functions of a single variable are usually just curves in 2 dimensions. So tangents there are straight lines anyway. So therefore, when we generalize this to 2 dimensions, you can see that your x-axis is along this line, your y-axis is along this line. And let's say we have a function of those 2 variables, x and y, and the output of that function is along the z-axis. Now, clearly this creates a surface. And thinking about tangents of surfaces as lines doesn't really make too much sense. At the outset, it doesn't sound very convincing. In fact, if you think about it, any tangent to a 3D curve should be a surface, it shouldn't be a line. But nevertheless, we saw some representations of how we can calculate line tangents to curves. So we're going to try and see how that really works. For this exercise, we're going to use this particular curve as an example. This is called Ricker wavelet. It's also called the Mexican hat because you see that the shape of the curve looks like a sombrero. And there's no specific reason I have chosen this curve beyond the fact that it's not really a too boring curve. It's not like it's a curve that has just one maximum and flat everywhere. It's not like that. It has a global maximum over here. It has a bunch of local minima around its bottom over here. And then the rest of it is pretty flat. So let's take a look at how we can find tangent lines specifically to begin with, to this particular curve, given what we have studied in the theory. So let's go back to Jupyter Lab. We are going to take the help of Python as well as GeoGebra to do this. So when we talk about scalar valued multivariate functions, those are typically functions of this form, x and y. You give 2 inputs, x and y, and you get one output. Let's simply call it z. And then we say that the tangent to a function f of x and y at a given point, which is a1 and a2, along some unit vector u, which has the coordinates of the x-axis and y-axis respectively, ux and uy. They are given by these 3 equations. X of t is a1 plus t of u1, where a1 is the x-coordinate of the point at which you're looking for the tangent, and u1 is the x-coordinate of the unit vector along which you want to find the tangent. Also, y of t is a2, which is the y-coordinate of the point at which you're looking for the tangent, and plus t times u2, where u2 is essentially just ui. Actually, I made a mistake here. This should have been ux and ui. And then finally, we have z of t, which is just the function evaluated at the point a, which is simply f of a1 and a2, plus t times f sub u of a1 and a2. Now, this f sub u is simply the directional derivative of f at a1, a2 along u. And it's defined as follows. You can simply compute it by taking the gradient of f of a1 and a2 and take its dot product with u. So this is just the standard inner product or the standard dot product. And this is interesting because you see that the gradient of f, since f is a function of 2 variables, it's going to give us 2 functions. The gradient with respect to x is a different function, and the gradient with respect to y, partial derivatives, specifically with respect to x and y, are 2 different functions. What you do is simply evaluate both of them at a1 and a2. So that's going to give us 2 values, and those 2 values make up a vector, and we know that the unit vector u is already a vector of 2 values. So it should be possible to compute a dot product that gives us finally a scalar value, right? And this is essentially just the expanded form of that. You take the partial derivative of f with respect to x, evaluate it at a1 and a2, multiply that by ux, and then you take the partial derivative of f with respect to y, we evaluate that at a1 and a2 and multiply it with ui, and we just add those 2 numbers together. So that's f sub u, a1 and a2. So let's go ahead and see what I'm sorry, I seem to have forgotten how to do the inputs. And there we are. Let's just create 3 symbols, x, y, and t, because we're going to need them later. And there we are. So this is the expression of the equation that we want to analyze. We want to find out tangents for it, and this is how you simply put that equation in Python, and there it is. This is essentially a simplified form of the equation. I know it really doesn't look simplified. A note here, we are using a library called SymPy, which stands for Symbolic Python, which lets us deal with symbols rather than the standard data types that we are accustomed to within Python. Like, for example, you can't do x plus x equal to 2x in Python, because Python would say that I don't know what the value of x is. So you'll first have to give the variable x some value, and only then you can do certain operations on it. SymPy makes it possible so that we can simply create a symbol called x, and then later just do operations on that symbol, and then do a bunch of different arithmetic on it. For example, you can do integration, differentiation, a bunch of different things you can do with SymPy symbols. And then when you want to evaluate that function, any function of x later, that's when you can substitute the value of x to be some integer or a float, and then you'll get the real value. Right? So SymPy enables us to do all of this algebra within Python, right? And that's the expression for it. Again, like I said, it doesn't really look simplified, but that's because SymPy's simplify method is not exactly identical to what we get here. But you can check for yourself, these are actually the same equation. And so that's what we do. We go to GeoGebra and we just plug the same function in. And you see that GeoGebra has plotted this curve for us. It's the same function, right? Now, all of this math, let's take a look at what we need to do this. We already, might know A1 and A2 because we would be evaluating the tangent lines at a particular point, and we would know U1 and U2 as well. We would know along which direction, along which unit vector we want to figure out the tangent, right? And other than that, we just need the f sub u expression, right? So I'm just going to write a function which is simply called solve. It takes in a function f, which is just fxy over here, and it takes in two other parameters. We tell it where we want the tangent, that's at, and in which direction or towards which direction we want it. So let us say that we want to find the tangent to this function at okay, let's pick the simplest possible point, which is this global maximum, and as you can see, that's the point at the origin with the z-axis value of 10. So we can say that it's 0, 0, and since we already have a function called f over here, we can simply say f of 0, 0, and there it is. GeoGebra helpfully labels this new point as a, which is 0, 0, 10. So that's the function, and we want to find the tangent lines at this function. Let's say we want to find it along the x-axis, the positive x-axis. And let's try and see how we can use this function to solve that, to figure out what the tangent should be. Now we know from theory that the tangent line is going to be a collection of three equations. Now let's see if we can print out those three equations. So let's say that, first of all, let's define this function. I run this cell, and let's say that I want to solve fxy at 0 and 0. That's the point at which I want to find the tangent, and I want to find it towards 1, 0, which is the unit vector along the x-axis. And you see that it gives me three expressions. Now these three expressions, the way that I've written the function, I've just printed out the three expressions in this order. So essentially what this means is x of t is t, y of t is 0, and z of t is 10. Now the question is, what is t? And the answer is that it's a parameter. You can just vary t, and it will give you different values, and the set of these different values should mean something. Now there's a very interesting way in GeoGebra where you can simply take parameters. So let me call my parameter with, let me initialize my parameter with some random number. Let me just call it 2, for example. And we know that the first expression is t, which means x of t is t. So I can just say x equal to t. That, as you can see, gives us a plane. The second equation is 0, so y of t is 0. Let me just split this window out so we can see both windows properly next to each other. Let's resize this a bit. I'm sorry. Yeah, there we go. let's also zoom out a bit so we can see everything properly. Yeah, so we saw that y of t is 0, so let me just put in y equal to 0. That gives us another plane. And then finally we saw that z is simply 10, so let me plug that value in as well, and I say that z is 10. So you see that we got 3 intersecting planes. Each of these 3 expressions, specifically these 3 equations, when we evaluated it for a1, a2 being the origin and u1, u2 being the unit vector in the direction of the positive x-axis, we ended up with these 3 expressions: x of t is t, y of t is 0, and z of t is 10. Now let's see what these 3 points together really represent. Let's maximize this a bit. And you see that GeoGebra also has a very convenient way of figuring out where 2 objects intersect. So we can just go to tools and say that I want to intersect 2 surfaces. Let me take this plane and then this plane, and that's it. So this blue dot vertical line that we see is the intersection of those 2 planes. Now I have that intersection, and let me see which are the, yeah, so I have just removed the planes which allowed us to come to that intersection. Now that we have that intersection, we don't need those 2 planes anymore. However, we still have the z expression to deal with. You see that this straight line also intersects the z equal to 10 plane at some point. So let's also try and find the intersection of that. And there too we have an interesting way of doing that. So it says, okay, select intersection or 2 objects successively. So let me select this object and then this object. And there you see that it's created a little point called B. So let me remove H as well. So you see that B is now my point. And here's the trick. When I vary t, B moves. And you see that it is moving along the x-axis. So as I vary t, it moves along the unit vector at which we created the tangent, at which we tried to evaluate the tangent line, right? And that's it. And if you look at simply, in fact, let me remove this as well because we still just have the point B. Yeah. So as we move B along, as we vary t, so essentially if we go back to our set of equations, you see that if I just vary t over the set of real numbers, I get a straight line. For a fixed value of t, let's say minus 2.3, my point B is something minus 2.3010, right? But as I vary p, you can see that it's bounded between minus 5 and 5, but it doesn't really matter because no matter how large I make this particular interval, it's going to, stay on the same line. And that kind of makes sense because you see that the tangent to the curve at this point along the y-axis is exactly the line along which B is varying, right? And all the analysis that we have done here and all the code that we have written here, which is again based on these formulas, is what has allowed us to do that. Now let's try to solve it towards another direction. So let's say I want to solve the same thing at 0, 0, but this time I want to do it along the y-axis. So let me put in 0, 1. And then again we get 3 more expressions. We see that x of t is 0, y of t is t, and z is again 10. So let's plug those things back in as well. So here, let me just go down and make this a little better so that we can still see most of our things. Yeah, and there we are. So we have x of t is 0, so I'll just punch in x equal to 0. Again, gives us a plane, and then y equal to t, which is this value, gives us another plane, and then z equal to 10. Now we've already seen this plane before. It's the same as above, and there we are. So let's go and try and figure out where we get another point, yet another point. So we go back to tools and we say we want to look at the intersection of 2 surfaces. I take this surface, and that gives me another line. And let's go back and let's remove the 2 surfaces, and of course you see that this line also intersects with the plane z equal to 10. So let's go back and look at the intersection of that as well. So I want to look at the intersection of this plane and this line, and that gives us a new point C, right? So let me get rid of this plane also, and we see here, in fact, let me see if I can get rid of that line as well. Yeah, there we are. So there we are. Those are our 3 points well, B is basically a point which varies along the line which is in the direction of 0, 1, 1, 0, which is the x-axis. C is a point that varies in the direction of this time 0, 1, which is the y-axis. And one of the good things about GeoGebra is that they color code their axis, which make it somewhat easy to remember. You see R, G, and B. So red, green, and blue, which all correspond to the x, y, and z axis. And you see that again when I vary t, both my points are moving. Both B and C are moving. So there it is. So simply by varying t, I am getting two different lines, right? And since we are also interested in finding out the tangent surface, not just the tangent lines, which we've already done, the lines along which B and C are moving are the tangent lines, but we also want to find the surface, we can use yet another tool. And we have something about planes here. There we are. So we can, make it find a plane through 3 points. So let's select that. And it says select 3 points. So let me select B and C as the first 2 points. And obviously A also lies on the same plane because A is the point at which we want to evaluate the tangent. And obviously the point at which you want to evaluate the tangent has to lie on the tangent, right? And we only need 3 points to draw a plane. So there it is. That's our plane. And there it is. This is basically the equation of the plane. If you simplify this particular expression, you'll just see that it's z equal to 10, right? And that is the tangent surface at this particular point. Now, how were we able to simply figure out that surface? Simply with the help of 2 directions. We computed the tangent line with respect to the x-axis, the tangent line with respect to the y-axis, or specifically in the directions 1, 0 and 0, 1, the unit vectors 1, 0 and 0, 1, we were able to figure out where this plane should lie. And the answer to that question actually is how were we able to figure out the plane just by using these 2 lines. We can just go back to our linear algebra lessons, and there we saw that any 2 vectors that are not parallel can span the subspace which is their dimension. So essentially these 2 vectors were orthogonal to each other and therefore they can span this entire space. Technically speaking, this is not a vector subspace because it doesn't contain the origin. It's an affine subspace, an affine flat. Anyhow, so this is how we found the tangent at the global maximum. Let's see if we can find the tangent at an arbitrary point. So let's just get rid of all of this and go back simply to seeing our surface. So I want to change my point A now for, let's pick a point somewhere here. So that appears to be something like 6. So let me put something like 6, 0 and f of 6, 0. So now my point A has gone all the way down here. There it is. So if we look at it, it's sort of at the bottom of the value over there. Not quite at the bottom, just a little to the left of it. But nevertheless, that's our point. And that's the point at which we want to find the tangent. I imagine it will be something like this. Let's try and apply the same process. We want to find the tangent line, which is in the direction of the positive x-axis, 0 and 1. So note that our A1, A2 is now 6, 0. So let's again just paste this equation over here and we say that we want to solve for fxy at 6, 0 towards the positive x-axis, which is 1, 0. And okay, that's a really weird looking equation, but let's see. It gives us x as t plus 6. So let's put that in. X equal to t plus 6. That's a plane, okay, some plane. And y is 0. Y is 0. And this is interesting. Let me just see if I can simply copy that and paste it as z. Z is that. Because some characters didn't get pasted correctly. That was the symbol t. And there it is. Right? So I hope that worked. Let me reduce the number of digits after the decimal. Yeah, it's 0.90 plus let's say 4.06 minus 4.06. So let's just simply call it that. Yeah, just to make it look a little better. And there we have it. We have our 3 surfaces. Let's follow the same procedure again. What we're going to do is look at the intersection of two surfaces. Let's take these two, that gives us the straight line, and let's try and remove those lines. There it is. So we have that line, and we still have the plane left by the Z. Excuse me. Oh, I think we accidentally added Z twice. So let me just remove this. Remove that. And now we need to find the intersection of this plane and this line. So let's go back again, and here we're going to say that I want to find an intersection. So where's that? There it is. So I select the plane and I select the line, and there's my point D. And you see that D itself also depends on T, the parameter. So let me just remove the plane, remove the line. There seems to be some plane which is still appearing, and D is there, but although I can't seem to get rid of this plane over here. Anyway, so you see that this point D, which is somewhere over here, and this was our point A at which we wanted to get the tangent. Let's see what happens to D as we vary the D. So you see it is actually in the expected direction, and D actually moves, if you look at it from this angle, it moves in the direction of the x-axis. It's moving exactly along the x-axis, and if we are not convinced, we can take a top-down view and see that D is actually again moving along the x-axis, because we computed it in the direction of the positive x-axis, right? So there's our D. That is one tangent line to the surface at the point E. Just trying to figure out how we can get rid of this extra plane surface, but anyway, I think that we can wait for it. We'll figure that out later. Yeah, so that's our D. Now let's also try and compute it with respect to the positive y-axis. So when I put this in, I just change the order of 0 and 1 here. So that's the unit vector towards the positive y-axis, and there we are. We get x equal to 6, y equal to t, and z is minus 4.06. So let's punch those in as well. We'll say that x equal to 6, and we have y equal to t, and we have z equal to minus 4.06. And there we are. We see that when we maximize this again, it's given us essentially 3 planes. So what we need to do first is get the intersection of these 2 planes. So let's go back and say that we want to get the intersection of that plane and that plane. That gives us the line. So let me remove the x and y planes again. And there we need to find out the intersection of this line with again the same plane as earlier. So we go back to tools and we say we want to intersect this object with this one, and that's our line E. So again, when we try and let me get rid of this as well, and when I try and change T, you see E also moves. Let's see if it's actually moving along the positive y-axis. It is. You see that red is my x-axis. Remember the RGB ordering. So you see that D moves along the x-axis and E moves along the y-axis. It's at least moving in a line that is parallel to the. So there we are. We have our 2 points, one moving along the x-axis, one moving along the y-axis, and then let's go back and try and figure out a plane which contains these 3 points. So let's, just so that we see things a bit clearly, let's remove the original function surface for a while. Let's go back here, and we want to see that we want to pass a plane through 3 points. So one of these is D, one of them is A, one of them is E, and that's our surface. When we go back and superimpose the original function on it, we see that while the points A, D, E could keep moving, they all describe, well, A doesn't move, E and D keep moving, both of which describe just one line along the plane, and together they make up this plane, which is the tangent to the surface at the point A, 6, 0. So that's how this works. Essentially, when we speak of tangent lines to a three-dimensional surface at a particular point, we don't just standalone speak of tangent lines. They have to be along a certain dimensions. And that makes sense. When I say that I want to find a tangent to this curve at this point, natural question to ask is along which dimension? We want it along the positive y-axis or the negative x-axis or some other arbit dimension. And the trick is that all of these tangents along many different directions, when they're put together, when they form a plane, that's when we speak of tangent planes instead of tangent lines. So I was having some trouble reconciling this idea of how tangent planes work versus how tangent lines work. So this is a humble attempt at making the explanation a little clearer. Thank you.